Can you do this? What is this? It is specs. The spec is made by using lenses. These are the lens. When you go to the spec shop and want to make some new specs for you, so first of all you will ask what is the power of the lens. So power of the lens is nothing but used to design the specs. Wherever the lens are there, lens are not used only in the specs. Lens can be used in making cameras, in optical devices. So many places we are using lenses, and while talking the lenses you need to talk about power of the lens. So in today's video we are going to learn what exactly power of the lens, how to measure and how to increase the power of the given lens by using combination of lenses. Stay with me. We got here three figures, figure 1, figure 2 and figure 3. In figure 1, the ray of light after refraction is passing through the focal point. In case of figure 2, the ray of light after refraction passing through the focal point. In the figure 3 also, the ray of light undergoing refraction and passing through the focal point. What is the difference between these three figures? In all the three figures, the difference is the bending. In the figure 1, the light is bending less. In figure 2, the light is bending more. In figure 3, there is the largest bending. The ability of the lens to bend the light after refraction is studied with the help of power of the lens. In figure 1, there is less bending and the focal length is larger. In figure 2, there is a little more bending but focal length has decreased. In figure 3, there is the largest bending but the smallest focal length. So the bending of light is related with power of the lens. More the bending, less the focal length, and less bending, more the focal length. So focal length and bending of light are inversely proportional to each other. The ability of bending of light by given lens is nothing but called power of the lens. From above discussion, it is clear that lens with shorter focal length bends the light more. Now let us develop the formula for power of the lens. To develop power of the lens, let us consider convex lens and a ray of light parallel to principal axis, and delta is nothing but angle of bending of light. Now from figure, tan delta is nothing but opposite upon adjacent side, that is h upon f. Let us take the value of h equals to 1, that is h is nothing but unit distance from optical center. Therefore tan delta equals to 1 upon f. If delta is small, then tan delta is equals to delta. Therefore delta equals to 1 upon f. This value of 1 upon f nothing but called power of the lens. And commonly it is denoted by letter P. Therefore power of lens P equals to 1 upon f. So now let us define power of lens. Power of lens is defined as the tangent of angle, that is a tan delta. tangent of angle. So tangent of angle of bending, delta is the angle of bending. This is a delta, and that is the angle of bending of light after refraction. So power of lens defined as the tangent of angle of bending by which light either converges or diverges. In case of convex lens, it converges, and in case of concave lens, it diverges. So power of lens can be obtained for both convex lens as well as the concave lens if incident light is parallel to principal axis. The important condition is the incident light must be parallel to principal axis. So if incident light is parallel to principal axis at a unit distance from optical center, that is a h value. The h value is equals to 1. So h equals to 1, nothing but distance of incident light from the optical center, the parallel distance. So this distance h is equal to 1. So this distance is equals to 1. So let us finally read the power of lens. Power of lens defined as the tangent of angle of bending by which the light either converges or diverges if incident light is parallel to principal axis at a unit distance from the optical center. It is clear that P equals to 1 upon F. So power of lens inversely proportional to focal length. That is the first observation. And lens with shorter focal length has higher power. That is the second observation. And lens with larger focal length has lesser power. This is the third observation. Power of lens is measured in diopters. Diopter is the SI unit. SI unit of power of lens. Now one more thing, the power for converging lens is positive and the power for diverging lens is negative. That means the value of D for converging lens is positive and for the diverging lens it is negative. If a person is having far-sightedness, then he will wear the glasses of positive diopter, and if a person having near-sightedness, then he will wear the glasses of negative diopters. Suppose we got the two lenses, we combine together, then the power of lens will also increase. So we can combine the lenses to increase the powers. Let us derive the one formula to find the combined power of two or more lenses when they are in contact with each other. These are the two lenses, lens A and the lens B. We do consider them as the thin lenses, so that what happens, the optical center of both the lenses will be exactly in contact with each other. So lens A and B are in contact, and we need to find out the total power of the lens after combination. Now let us complete the ray diagram. O is the object, I1 is the image produced by the lens A, and I1 becomes virtual object for the lens B, and I is the final image by the lens B, and P is nothing but center point of combination. This is the point P, that is the center point of combination. Now applying lens maker formula for the lens A and the lens B. Lens maker formula for the first lens, 1 upon V minus 1 upon U equals to 1 upon F1. What is the U? U nothing but object distance, and F1 is the focal length of the first lens, and F2 is the focal length of the second lens. Similarly, applying lens maker formula for lens B, that is 1 upon V minus 1 upon V1 equals to 1 upon F2. Call it as equation 1 and equation 2. Adding equation 1 and 2, so 1 upon V1 and 1 upon V1 get cancelled. So we get 1 upon V minus 1 upon U equals to 1 upon F1 plus 1 upon F2. But 1 upon V minus 1 upon U is nothing but 1 upon F. F is nothing but resultant or combined focal length of the lens A and B. Let 1 upon F equals to P. So here is the 1 upon F. 1 upon F equals to P here. Therefore we get P equals to P1 plus P2. What is P1? P1 nothing but 1 upon F1 equals to P1, where F1 is the focal length of the first lens. And what is P2? 1 upon F2 is equals to P2, where F2 is the focal length of second length, that is the lens B. So P1 is the power of the lens A and P2 is the power of lens B, and total power is nothing but addition of power of first lens and the power of the second lens. Thus, when we combine the two lenses, then the power of lens equals to P1 plus P2. This is the total power or equivalent power after the combination. Suppose we take the three lenses or the four lenses, then P equals to P1 plus P2 plus P3 plus P4 and so on. For the n lenses, it is a P equals to P1 plus P2 plus P3 plus P4 up to the n. So Pn. So thus we can combine the any number of lenses, then the total power is nothing but addition of individual powers. So this is the way we can find out the equivalent power after a combination of lenses. That's all in this video. I hope your concept regarding power of lens have been cleared very much. What else you want to watch on this channel? Let me know. Write down your comments in the comment box. Meet you again with another topic. Till then, wish you good luck. Enjoy the physics. Bye bye.